at this Bayesian networks, we also have an evidence. Evidence is a green one over here. And we have a conditional probability table for it, which I filled somehow. So we have three potential values for sensor, like detecting that the wall is 1 meter away, 2 meters away, and 3 meters away, right? And for the location 1, angle 0, the sensor will read 1 with 50% probability, will read 2 with 30% probability, and so on. For location 1, angle 3, it will read 1 meter with 20% probability and 2 meters with 60% probability, and so on, right? This resembles a lot with your problem from milestone 1. So this is a static belief network. Any question about this so far? Good. Then you have milestone 2. You need a transition property model, right? So we have an action, rotate right. This is the action. The only action available here. Obviously, with your robot, you have multiple actions. So we have the rotate right having an impact on location. So you have here condition probability table to move from location 0 to location 1. So you have for location 0 the prior. Rotate 0, it's an action, it's an evidence. This is what we mean by an action. An action is a random variable, just as until now, just with as with evidences and hidden states. It's a random variable. The difference between an action and an evidence is an action, it's a parent. It's a parent in our belief network. So belief network is a transition, okay? And to denote that it's an action, I'm not going to use circles, but squares. And in this set of slides, they are orange squares, okay? So let's see the priors for location are given over here. For rotation, the value is given. So it's the value of the random variable rotation will be something like true with 100% probability and false with 0% probability when we know that we rotate, and vice versa, true with 0% probability and rotation, false with 100% probability when we know we don't ask the robot to rotate. And we have the transition probability table. Is the kind that you are getting from your so the CPT, condition probability table for the transition for location 1 given the rotation action and the location before. And this is the one you are building in this milestone. Like it's the order rotate was given and the location was 1. Then you still remain in location 1 with 1%, 0.1% probability, 0.1 probability. That's 10%. Sorry. You move to location 2 with 70% probability, and location 3 is not shown over here, but you know it's 1 minus 2, so with 0.2%, 20% probability, 0.2 probability, you move to location 3. Location 3 is not shown as typically with condition probability tables. The same if there was no. Because you have 3 locations, 1, 2, and 3. And 0.1 plus 0.7 plus 0.2 adds to 1, right? So 0.1 plus 0.7 plus, okay, 0.2 equals 1. So you have 0.2 for the hidden column in the condition probability table. Okay, so the same for all the other entries. If there's no order to rotate and you're in location 1, then you remain in location 1 with 60% probability, move to location 2 with 0.3, and to location 3 with 0.1, and so on. We also have a similar Bayesian network for the transition of angle. So we have the prior value of angle over here, and condition probability table for angle 1 given the order to rotate and the previous value of the angle. So if you told it to rotate from angle 0, it will arrive in angle 3 with 70% probability, in angle 6 with 0.2. And when the numbers are a little bit similar, I lacked imagination, but you are computing it from your measurements, and you should get much more different values, right? So this is the transition probability tables, like the ones, like the belief networks you are building now for milestone 2. But you are going to get much larger tables because you have much larger set of values for your random variables, and the condition probability tables look also much richer. Any questions so far? No? Okay. Let's go on.
Can we go back? Can we go back to the slide, please?
Yes.
Yes. Yeah. Okay. So for here, what do you call it? For that column, we are assuming that what do you call it? What are we assuming with the what do you call it? The initial location. Why? I mean, what? And that's what you.
When you have placed the robot, you know, when your system starts,
yeah,
you are placing the robot somewhere, right?
Yes.
You may know where the robot is, or you may not know. It depends on the problem. If the robot doesn't know where it is at all, then you are going to have a uniformly distributed probability, like here, like 30%, 33% in one, 33 in the other, 33 in the other, right?
Yeah.
Location. Or in your problem, you may be told the robot starts from the charger, and you may know exactly where the charger is in your room, and then you'll have 100% probability to be there and 0 for the other location. So there's always a prior probability that it's available, can be uniform or very specific. And then you have the condition probability table that describes where you arrive after the set of actions you are taking. Is that clear?
Yeah. But wait, but basically, what I was trying to what I was trying to understand was like it is not. What I was trying to understand was why it was not like part of like why it was not part of the probability.
Who?
What do you call it? Location 0.
The prior.
Yeah, not yeah. Okay. So before we take, so we are. For that conditional CPT, I'm guessing that we assume. I mean, we are assuming for true. What do you call it? What are we like? If it does rotate right, we are we are assuming the left sonar reading 1, left. What do you call it? The right sonar reading 2. I mean, and then the right sonar. What is it called? Oh, okay.
Is this what we're asking? So the first row here is location 1, 2, or 3, and the second row is the probability of the location being at that position. Okay. Was this was not clear?
And also, I also tried to understand the CPT over there next to R. The action is true, false. Why do we have what you call it, the location 1, 2, and 3? That's what I'm trying to understand a little bit. After the action has been after the action is true, why are we so we are still assuming that it is still at 1? I don't know if I'm being understood.
In this case, it's given that you're starting at location 1.
Yeah, right? But yeah, is given that we're starting at location 1, but then we take the action, and then it's what do you call it? We are still at location 1.
You could be.
We didn't know that we are at location 1. I mean, I draw here a drawing with a possibility. There's a probability that you're at location 1, but we said we don't know. There's just a prior probability. You may be at location 1 with probability 30%, right? But we don't know that you are at location 1. We don't know, we may not know where you are. That depends on the problem. In some problems, you know, as we said, if you know that you start from the charger, then you know where you are, but you may not know. That's something that's depending on the actual query. So we build a model that should work in any situation. So what we care is this condition probability tables. This is what is part of our design. The priors are part of the query. So when somebody uses your program that you write, it's saying, okay, the robot starts from the charger, that it works. So it's basically telling the robot it's at this location with 100% probability at the beginning in location 0. Or it may say, we don't know where the robot is. The robot is waking up. Go on and find where it is.
Okay.
So the robot should be able to find its way based on other situation, but we don't tell where it starts. That's a problem specification. What we are saying is a model. So the condition probability tables, this is of location 1 here, the big ones. These are the ones that are actually relevant.
Okay, so we don't know where the initial location was, and then after we take the action, we still do not technically know where the location is, but we going to calculate
we know a belief. We know a probability distribution where over where he was, and after the action, we learn another probability distribution over where it's going to be. And this condition probability table is telling us a new probability distribution of where the robot is after the action.
Okay, because I'm struggling to understand like how we come up with the this transitional probability.
You measure it. This is your milestone. You take the measurements. You see the measurements of your colleagues from last year. So you have 10 rounds of running with from location 1 with order move, and you measure where it arrived. It arrived probably 100% of the time in location 2, or 80% of the time, and you record those numbers.
Okay. All right. Thank you.
Okay. Is it clear now? Is it clear for everyone? Godwill, is it clear now? Okay. So you come up with these tables by taking the measurements of your colleagues from last year. You just count. You say 10% of the times it landed in 1, so 0.1, 70% it landed in location 2 when it was in location 1 at the beginning, so you have here where it was and where it landed, and that's it. Okay. No more questions here. We can go to the next. So based on these two Bayesian networks, we compose two sets of Bayesian networks, the static one and the transition ones, and we get a full dynamic belief network. The full dynamic belief network looks like this. So based on location 0 and angle 0, you have the Sonner measurement at the beginning. Then you have an action rotate right, let's say, that can be true or false. Based on it, you are going to have a new set of angles, angle 1 and location 1, with their condition probability tables copied from the previous one. So all these condition probability tables, since we assume a stationary process, they are going to be always true for angle 1, location 1, and the condition probability table from the static one, the one here below, this is going to be replicated here as condition probability tables for Sonner 0, Sonner 1, and all the other in the future based on the stationarity principle. Okay, so this keeps being replicated like that. From angle 1, location 1, you have a rotate right action 1, and that goes further to angle 2 and location 2 and Sonner 2 and so on. Any question?
Just, I mean, I don't think it's a question, but just to clarify, so this is for one action. So that means that if you're doing it for, let's say, multiple actions, that means every single action that, how does it become nested? That's what I want to know.
Well, if you have an action, many actions can be seen as one action if you want in the extreme theoretically. So the action is go to the right, turn your head, and do something like that. So you could build a random variable action, which is composed of all possible ones, or you could simply build a smart Bayesian network here that has all the relations related to your actions, as many as they are. The better, the more sparse your matrix is, the more efficient your computation.
Okay.
Okay, so yeah, you have more actions, you just have an additional rectangle here and the arrows that correspond to it. Is that clear?
Yeah, and let's say I rotate right. That's just it. I rotate right, and then
Yes.
I have my CPT, so I can calculate where location I am, and then I decide to say
you don't calculate where you are, but you calculate the probability distribution of where you could be after that action.
Yeah, and then I take another I take another action.
Right.
Does that if I take another action, that means like if I'm sampling data, does that mean that I take the data from where I was initially? That if I take example, if I was in 1, and let's say I rotate right and I somehow ended up in 3.
Yes.
Does that mean that if I want to take another action, I also have to so that means I would have to take data from when I was at 3, when I rotated, let's say left, the probability of me landing in 1, the probability of me landing in 3, and now the probability of me landing in 2.
Right, so you never know where you are. The robot never knows where he is. You take action, rotate right, and you have a probability distribution. Very likely here you are not in 1. You are with 70% probability in 1, let's say, or with 40%, and with 30%, yeah, you take the action, rotate right, and you may arrive in 2 or in 3, but you have just a probability distribution of where you are. You'll never know where you are.
Right.
Okay, the same, the robot never really knows where it is. It's just a probability distribution, and you work with what you have. Yeah, that's it. Okay, so you see, this is a full belief network that we are getting from this kind of Bayesian network. Combining the milestone 1 that you get with the milestone 2, you get this at the end of this milestone 2, because you're combining the 2 Bayesian networks. Is it clear? Then we are going to take these Bayesian networks and we are going to run over them likelihood weighting. Okay, so we are going to run the likelihood weighting algorithm. Okay, so you are familiar with the likelihood weighting algorithm. It is here. So let's look at this matrix, this slide over here. We just take angle 0, location 0. In this situation, we'll assume angle 0, location 0 at the beginning, and we don't have any measurement before the action. If we had any action measurement before the action, we'll assume that this is for angle 1, location 1. It's one time later after we took the measurement. The action could be taking the measurement, so no rotation 0. We'll assume that the actions happen, and in the next time stamp 1, location 1, angle 1, we have a measurement sonar 1. And at the beginning, we had priors for angle 0, location 0, the original one. And now we are going to use likelihood weighting to compute the probability of angle 1 and location 1. Okay, we'll assume we don't have more than one time step. Okay, this is an algorithm we run after the first time increment. So the way we are running it, you are familiar with the likelihood weighting algorithm. Here I ran a sequence of random number generators, and I got these random numbers, 62, 87, and so on. And I started to sample from this Bayesian network. I told you you have to implement likelihood weighting, and this is what it does. In my case, I take 62, and I sample angle 0. You know, I had here 20% probability it was in angle 0. Let me have a way of doing it without bothering the camera. So I'm at 60. So the first random number here, it's 62. Then, which means below 20, it would have been 0. Below 20 plus 5, which is below 70, it's angle 3. Yes, 62 is below 70, so we say we are at angle 3. Clear? How we sampled angle? Then we are going to sample location 0. Location, we take the random variable, the random number 87, and we go here. Before 30 would have been 1. Before 60, 3 plus 3 would be 2. 87 is bigger than that, so we are at location 3. Clear? Is everyone clear? Okay. Yes, okay. Yeah, we'll do 3 samples. Then we'll go and sample angle 1. So we take the random number here, 50, the third random number. Yeah, I'm going to use the yellow. We'll take 50. And for angle 1, we have been at angle 3 before, and the rotation has been true. So we are sampling this, and we happen to be in the random number 50. So up to 30 it was angle 0, up to 40 is angle 3, and we are further, will be here because 50 is bigger than 40. So we are at angle 6, and you see here angle 6. Okay, then we are going to sample location 1, and again we are at location 3, action true, and now we are going to look, the random number here was 78, so that's up to 70 we are location 1, we are past 70, so we are at location 2. So here we are at location 2. And then we look at the sonar. We were at angle 16 location 2, so that's angle 16 location 2. And since sonar 1 equals true, equals 1, it's sonar 1 has value 1 meter, we are going to read this probability 0.1, and it translates into the weight 0.1. Now let's take sample 2. We go to the next set of random numbers. So 89 is the next random number. We sample angle 1. Angle 1 sample for 89, 2, 7 up to here. This is angle 6. It's angle 6. Then we sample location 0, 98. That's 3, 6. We end up at location 3. Then we sample angle 1. So we are at angle 6. We are going to sample with the random number 75. So we are here, and we say below 70 would have been angle 0, past angle 70, it's angle 3. So here we are at angle 3. Again, your question is, don't you need to put the last position probabilities? Last position probabilities. What do you mean? May I ask you to expand on your question, Samantha? Sam, can you hear me?
Okay, so if you look at the tables by angle 1 and location 1, you've got like the probability of angle 1 is 0 and probability that it's 3, and then you have probability of location 1 and then location 2. Don't you need to take...
Can you just repeat? So where do you see probability of angle 1?
No, we don't see angle 1. That's what I'm saying. Like we have 0 and 3, and so wouldn't you have to add that column because we're only considering these two possibilities right now, right?
So what you are looking, you know its parents, right? Because we have samples. So its parents are angle 0.6 and location 0.3. Right? This is what we have computed. We have sampled so far. And now we are using the random number 75 to sample angle 1. So, and we know that the action was rotate equals true, right? So we go to the row here in this table over here, in the condition probability table for angle 1. And we go to the entries for rotation action true and angle equals 6, the one that we have sampled so far in this sample, in sample 2. And then for the random number 75, we find the right entry. We know that if the random number would have been smaller than 70, we would have selected angle 0. But because it's bigger, it means we select angle equals 3 from 70 to 100.
Okay,
So
well, right, but that's where I'm confused. Like, so in that probability, you're not considering the probability that could be angle 2, right? Isn't there a range where you'd have to say that it's the angle of 2?
I said at the beginning of the problem that we have discretized the space, and we only have angles 0, 3, and 6 because we discretize the space. Like in your problem, you cannot, with your robot from the measurements of your colleagues before, you cannot have the angle 3 because we only used increments of 5 degrees, right?
Right.
Yeah, so that's what you have in your actual problem too.
Right, but go back to the slide you were just on.
Yep.
In your output probability there, you're only taking into consideration the probability that 1 is 0 or the probability that angle 1 is 3. We're not taking...
Yeah, I'm taking also the others, certainly. The probability it's here is 0.2 for angle 1 equals 6, right? Equals for angle 1 equals 6.
Yes.
You have .2 for the second entry is 0 because 7 plus 3 it's already 1. So it can never be here. It's .1 as the third column is .2 absent at the third row. Sorry, and as the last row, the missing number is .3 plus .2 is .5. So you have a .5 missing. So yeah, we also take that into account. It's just that your tables do not typically store the numbers, right? That's how we have learned at the beginning.
Okay, I guess I was just getting confused, but thank you.
Yeah, we are taking them into account. That's why we actually selected angle equals 6 in the first sample. You see, we had angle equals 6 here. Because last time we looked into that last column. We took it.
Oh, okay. Okay, thank you. I was wrong. Thank you.
Okay. Okay. So let's sample now angle 1. That's where we were. and we decided that angle 3 was matching. Now we are going to sample location 1. We take the random number. Let me take the yellow pen again, because otherwise we don't see what the number was. Okay, so the random number 21. And we are sampling location 1. As location 0, we have been in 3, so we are in location 0, 3, and this is the same as before. Therefore, we are at the same row, but the number is 20. 20 corresponds to location 1, so we are going to location 1. And the sonar tells us that sonar value 1 for the pair of angle 1 equals 3 and location 1 equals 1. So location 1 equals 1, angle 1 equals 3 is this row over here. And we know that sonar is 1, so 0 is the right, dot 2 is the right weight. Okay, clear?
Yes, thank you.
Okay. Where are we here? Okay, and then the sample number 3. I'm running the last 3 numbers. So for 33, I'm again sampling the angle 0 at angle 3 because it's 2 plus 5. Then the number 79, I'm using to sample location 0, and that comes 3 plus 3 is 6. 7 is bigger than that, 79, so it's again location 3. Then we sample angle 1 with the number 80. We are again in the same column for angle equals 3, which is the same row, rows 2, and the random number was 80, so we are again all at the end, and again we have the remaining 1 minus 3 minus 1, so we have again angle equals 6. And we sample with random number 94 for location 1, and we are based on location 0, 3, again the same row. So with the number 94, we are at the last location here, which will be 2. Okay, so we are at location 2, because 7 plus 3 is the second, is this particular column. And we look for angle 6, location 2 is the same as in sample 1. We are in the same column here, and the probability of our evidence is 1, so we put it in the weight, and it's 1. And based on these weights, we compute the new distribution for angle 1. So we see we got no angle 1 with value 0, so the probability of angle 1 having value 0 is 0. The weights for weighting for the angle 1 equals 3 is dot 2 out of the total mass at dot 4, dot 1 plus dot 2 plus dot 2, 1. This is the sum of this equals dot 4. So dot 2 divided by dot 4 is what we have the probability of A1 equals 3. And the probability of A1 equals 6, we have 2 of those, dot 1, with together sum with dot 2, also divided by dot 4. So we have that probability of angle 1 equals 6 is also dot 4. We normalize it and we get dot 5, right? And for the location 1 happened in the sample number 2, and that was the weight dot 2 divided by dot 4. location 2 happened in the sample 1 and sample 3, which was with weight dot 2 divided by dot 4, and location 3 never occurred, so we have probability 0. So the new distribution for location 1 is 0.5, 0.5, 0. Okay, so we get these two new priors for angles 1 and for location 1. So these are the probability of angle 1 and probability of location 1 now that we have measured SONAR 1 to be 1. And now we go to the next. Okay, to the next entry. And we replace in the next moment in time, we move from time 1 to time 2. We have the priors obtained in the previous computation. So angle 1 has probability 50% to be in the angle 0 or 6. Location is with 50% at location 1 or 2. And now at this time frame, we also have a rotation right value of true. So let's run a set of samples, 3 samples here with these random numbers that you have obtained now. Okay, so let's start with again an exercise with all of you one by one. Who goes